Hello, everyone. Welcome to Theo-MathProblemSolver. In this particular episode, I'm so excited to take you through the journey of numerical integration. In our previous episode, we kind of look at various situations by which we can leverage the concept of integration by substitution and integration by part. But in as much as sometimes we want to employ all of those techniques, sometimes they fail. And the reason is one of the reasons is because sometimes the antiderivative of the integrand may be almost impossible to solve or even to sort of apply it even directly. Okay. Also, another reason may be that the data may not be conveniently fit into a common function that can be integrated directly or easily. So in such a situation, we have to sort of resort to another powerful technique or method. And today that is the goal. Okay. Today we are going to look at a numerical sort of integration. And the numerical integration, what it does is that it helps us to get an approximate value of the area under the graph of a function within a particular, domain. All right. So one powerful tool that we are going to look at today is what we call the Riemann Sums. The Riemann Sums, all right. So with the Riemann Sums, with the notion of the Riemann Sum, what we are basically trying to say is that since it's almost impossible to calculate the area under the curve within a particular domain, what we are going to do is that we are going to, within the interval A to B, okay, within the interval A to B, we are going to subdivide this interval and then erect a rectangle on each subinterval, okay? Then what basically we are trying to do is that according to Riemann, it says that the more rectangle we're going to have under the curve, see the curve over here we have, there's a curve that we have, okay? Our curve is F, okay? And then it says that for us to have a better area, okay, a better approximation of the area under such a curve, what we're going to do is that we are going to have a lot of rectangles. It says that the more rectangles you have under the curve, the better the approximation. Okay, so that is what Riemann is saying, and that is what we are going to look at. All right, so how do we continue from here? So what we are going to do is that, let me just get rid of this one. So what we are basically going to do is that we have to, but then one thing we need to bear it in mind is that we have to bear that in mind that bear in mind that the width, okay? So the width, which in our case is going to be the base for each rectangle. So for instance, if we pick one particular rectangle, then the width we are going to consider will be B minus A over the number of partition or the number of subdivisions that we want to have. In our case, we are only considering four rectangles. So which means that our n will just have to be 4. Okay, so we're going to have B minus A over 4. Okay, good. Then what we are going to do is that um then what basically we are going to do is that the function values when we anytime, so it means that the height, so when we look at the first rectangle, so this is our first rectangle. This is our first rectangle. Now the height of this rectangle is just going to be our f of x1, okay? And then the height of the second rectangle will just going to be f of x2, and then the height of this rectangle, okay, when you trace it here, is just going to be f of what? X3, and so on and so forth. So I would say that the height, of this rectangle, so the height, of the rectangle will be f of x1, f of x2, f of x3, and then f of x4. So all of this will be a rectangle. So for instance, when you pick one of the rectangles, okay, so suppose we pick one rectangle, so it means that the area of one rectangle, so the area of one rectangle is just going to be what? the base. Remember, the base is just going to be the base. We said is the width. Okay, so they've said that this is the width. Okay, so the base is what we call the width. Okay, so the base is also one. The area of one rectangle is just going to be the base, which is the width times the height. Okay. But then since we are talking about area, you're going to sum all the areas, okay? The area of each rectangle. So we are going to sum all of that. So f of x2 plus the base times f of x3, then plus the base, which is the width times f of x4. Is that okay? Good. So that is what Riemann is saying. But then the various ways by which we can use Riemann to approximate values of some integral. Okay, so what I'm going to do, the next thing I'm going to do is I'm going to pick an example, then I would explain it better. So we have various ways that we can also look at it. Some would look at it from the, so for example, if you're within a particular interval, we kind of look at the open endpoint of each subinterval, then we use that as our height to use them as a value that we are going to plug into the main functions to get them as height, and some the other ways by which we can also use the right endpoints. Okay, then we substitute those values into the main functions to be used as height and in our computation. But the point of all of this is to lay the foundation. So I'll pick an example so that we understand what I'm trying to say. All right, so let's get going. So let me bring up an example so that we all understand it better. So suppose so let me look at the first example. So our first example, so example one. So example one. So with example one, suppose we want to find an approximate value of, so they find the approximate, oh, we want to find an approximate value of, this particular problem. Okay, so we want to find an approximate value of this particular problem. So what it basically means is that this particular integral may be very difficult. The integral may be very difficult to find its antiderivative. So we have to resort to a very powerful tool which we call the numerical integration. Okay, so how do we do that? So by using the Riemann sums, what it means is that we kind of have to look at the whole concept and see how best we can use that to solve this particular problem. All right. So the first thing to do, we need to look at the width. Okay. So the width. So remember the width. We need the width of the rectangle. The width we said is what, b minus a on n. Okay. But in this particular problem, let me be more specific before I move into the solution. Well, I want to state that the question demands that we use n, so using n equal to 6 equal size subintervals. Okay. Okay, so we have that. All right, so what is our b? Per the question, our b is what? Our b is the upper limit of the integral, okay, which is 3. and then our A is 0, and then our N, we're giving us 6, which means that we're going to have what? So we're going to have 0.5 as our weight, okay? So we're going to have this as our weight, okay? So on that note, we are going to look at the left endpoint, the left endpoint of the interval, okay? So we will write, or we will find the left endpoint. So we would find the left endpoint first. So let's find the left endpoint. So we will find the left endpoint, okay? So we will find the left endpoint first, okay? So with the left endpoint, what basically we are going to do is that, so remember that the interval is from 0 to 3, right? So since we have a width of 0.5 or steps out of zero point 0.5, it means that at every step point, we're going to have 0.5, right? Very good. So it means that we will start at 0. Then since we have a width of 0.5, we're going to have 0.5 here. Okay. Then the next one will be what? 0.5 up to 1. Then from 1 to 1.5. Then we have 1.5 to 2. And then from 2 to 2 point what? 2.5. And then from 2.5 to what? Um, 2.5 to 3 as our sub intervals. So these these ones they are sub intervals, okay? So we call this one the sub intervals. So this becomes the sub. Okay, and these sub intervals. What we're going to do, we're going to erect rectangles on them, on each, okay? On each sub interval, we're going to erect rectangles on them, okay? And that's what we are going to do. And I believe we are getting it right. All right. So the next thing we are going to do is that for us to make things as easy as it should be, I'm going to construct a table, so that with a table it makes it a bit easy to understand. So I would pick each sub interval, since we already have laid out a foundation to be easy for you to understand. So I'll construct a sub interval. So there's already a sub interval, so I've already done so I'm going to do that, and then I also pick the width, and then how best we're going to find the height, and then from there we can find the area. What then happen at the end of the day, what we're going to add all the areas together. Is that okay? Very good. Let's take note of that. So I'm going to say, we have a sub interval here. So we have a sub interval. We have the width. So we have the width. We have to also look at the height. So the height. Okay, then finally we have to look at, and the height, we want to say that x equal to the left endpoint, okay? So we're going to look at the left endpoint. So I'll explain that, and then we'll look at the area, okay? So this is what we are going to do. All right. So now, this is what we are going to do. Now, what we are going to do is that So when I pick one, the first subinterval, which is from zero to which is from 0 to zero 0.5. So the first subinterval is from 0 to 0.5. Okay. And then the weight, remember the weight we had was 0.5, where then becomes the height. Remember over here, we are looking at the left, okay? We are considering, over here, we are considering the left endpoint. We are looking at the left endpoint, okay? So we are looking at the left endpoint. So the left endpoint of this subinterval is what? Is 0. So what happens, I'm going to plug, I'm going to plug this 0 into the into the integrand. Remember, the integrand we're given was root of e to the power x plus 1. Okay. Okay. So let's take note that the function we're given was what? F of the integrand was what? Root of e to the power x plus what? 1. Okay. Very good. So we are going to plug that into, we're going to plug the left endpoint, which is 0, into the integrand, and that should give us what? It may just mean that wherever I see x, I should replace it by 0 into this. Okay. And that should give us what? 1.4242. And then what then becomes the area? Remember, the area of a rectangle is what? Becomes a length times what? The breadth, right? But the length in our case is the width, okay? And then the height becomes your breadth, okay? So we just have to multiply these two together. So the 0.5 and this value, okay? So that's what we are doing. So when you multiply them together, we're going to have so we are multiplying 0.5. We are multiplying 0.5 and that of 1.4242. And that should give us what? 0.7071. Okay. Now the next one we need to do is that we have to consider the second endpoint, the second subdivision. The second subdivision was 0.5 to 1. Okay. And remember, at this, what that we are doing is that we are looking at the left endpoint. So the second left endpoint is what? Is 0.5. Okay. So, and still we still have the same weight, which was 0.5. And then we plug this 0.5 into the integrand, and that will give us the solution. And that should give us what? 1.6275. Okay. So we multiply 0.5 by 1.6275. And that should give us what? When you use a calculator, that should give us 0.8135. Okay. Then we have to move on to use the second subdivision. The second subdivision, we're going to have this. Okay. Then we would use the left endpoint. The left endpoint is what? Is 1. Okay. Remember, the weight is still the same, which is 0.5. Then we plug 1 into the integrand. And that should give us what? That should give us 1.9283. Okay. Then the next thing we need to do is to dot the width and the height. Okay. So by multiplying the width and the height, we should have 0.9641, I think 5. Okay. The next thing we need to do is that the next thing we need to do is to pick the next subdivision, which is 1.5 and that of 2. And as usual, we pick the left end point, and that should give us what? 1.5. Okay. And the weight will still remain the same. Then we plug this value into the integrand, and that should give us 2.3413. And that when we dot the width and the height, we should have we should have 1.17065. Then we pick the next subdivision, which is 2 to 2.5, and the width still remain the same. Then we plug we pick the left endpoint into and plug it into the integrand, and that should give us f of 2. And by plugging that into that, we should have 2.8964. And then by dotting the width and that of the height, we should have 1.4482. Okay. And then finally, we look at the last, we look at the endpoint to be 2.523. And as usual, we pick the left endpoint. As usual, the width remained the same. And then what happened, that we plug in the left endpoint into the integrand, and that should give us 3.6308. And when we dot the width and then this height, we should have 1.8154. Okay, at the end of the day, what we are going to do, we are going to sum, sum all of the areas together. We're going to sum all the areas together. And when we sum the area, we're going to have the left endpoint. Okay, when we consider the left endpoint, the area is just going to be 6.691925. Okay, as the area. So this is what we are going to have as the area. Okay, so we're going to have this particular value as the area if we are using the left endpoint. Now, at this point, what I want us to look at now, we're going to look at the right endpoint. So let's consider the right endpoint. So now we know the left endpoint, but now let's consider the right endpoint and see afterwards and see what will happen. So at this point, we are considering the right endpoint. So we are also going to build the same table, but this time around, we are going to use the right endpoint instead of the left endpoint. So we are picking the same subdivision, okay? We are considering the same subdivision. So we are having the subdivision. Let me take my time to write this well. So we have the subdivision, we have the width, we have the height, and then we have the area. Now, as usual, we had our width, our first subinterval from 0 to 0.5, and then our height was 0.5. So since we are, since we are considering the right endpoints, it means that we are going to pick 0.5 instead of 0. Remember, what left endpoint we pick 0, but because now we are considering the right endpoint, we are considering 0.5. Is that okay? Then we plug it into the main function, into the integrand. Remember that the integrand was e to the power x, root of e to the power x plus 1. Okay, so 0.5 here plus 1, and that should give us what? That should give us 1.6275. Okay. Then we dot the width and that of the height together. When we dot them, we should have 0.81375. Okay. Then the next subdivision, we're going to have 0.5 to 1. Then we pick the right endpoint, which is 1. Okay, and then we know that the width still remain the same. We plug 1, okay, into the integrand, and that should give us what? That should give us 1.9283. Then what happened is we're going to dot the width and that of the height, and that should give us 0.9 6, 4, 1, and 5. Is that okay? Then we pick the next subdivision. With the next subdivision, we're going to have 1 to 1.5, and then the width still remain the same as 0.5, and then we plug in the right endpoint, which is 1.5, into the integrand, and that should give us what? That should give us 2.3, 4, 1, 1, 3. No, 1, just 1, 3. Then we dot the width and that of the height, and that should, give us 1.1706. Then in the next interval, we're going to have 1.5 to 2, and the width still remain the same. And as usual, we plug the right endpoint into the integrand, and that should give us what? That should give us 2.8964. Then we dot the width and then the height, and that should give us 1.4482. I think when you use the calculator, you should be able to find the same thing. So the width will remain the same. And as usual, the right endpoint, we have 0.5. Then we plug in 0.5, and that should give us 3.6308. Then we dot this and that should give us 1.8154. Then we pick the last interval, and that should give us 2.5 to 3. The width still remain the same. We pick, as usual, pick the right input is 3. Then we plug it into the main function or into the integrand, and that should give us 4.5919. And then when we dot this and that should give us 2.29593. Okay. Then what that we need to do is that we are going to sum. So we are going to sum the area together. Okay. So we are going to sum the area together. So with the right endpoint, we find out that the area is just going to, so we just add all these areas together. So we add all the areas together. Okay. So by adding them, we should have 8.5081. Okay. Then what we are going to do is that we are going to find the average. Okay. So we take the average. Then finally, we are going to take the average. Okay. We're going to take the average of the left endpoint and that of the right endpoint. Okay. So the average of that gives us the area under the curve. Okay. Remember the first one with the left endpoint, we had 6.6919. 6.6919. Then we add it onto the right endpoint. We had 8.501 all divided by 2. And by my calculator, we should have, let's see what we had here. 8.5081. Then we divided by 2. Then when we divided by 2, we had 0.96919 plus 8.5081. Then we divided by 2. Then we have 7.6. So when we add the 2 together, we have the area, an approximate area under the graph of the function to be 7.6. So we have the area to be 7.6. Okay, so we have this to be 7.6. But I want to, kind of stress that this is just an approximate value of the area under the graph of the function. Is that okay? And at this point, if you have not subscribed to my channel, please do so. Let's help, grow this channel together. Please, the whole point of this, platform is to create a community where the whole point is to try to demystify the myth around mathematics. So help, share this content with your colleagues, with your loved ones, and also turn on your notification button so that anytime I release new content, you will be the first to receive that. Thank you so much for your time. In our subsequent episode, we'll be looking at other interesting numerical integration methods and techniques as well. So stay with me.